Cisco Certified Network Associate Day 24. Welcome back everybody, I am Imran Rafai, your trainer for this entire series. Today we are going to look at IP version 6. Now IP version 6 has been part of the old 201.20 CCNA, or which is known as the version 2 of CCNA, but version 3, the 201.25 exam, has in-depth IP version 6, right? So IP version 6 has been a very beautiful technology that has been in implementation for a very long time, but for some reason it has been delayed, and we will be looking at some of the aspects what happened and the reason why IP version 6 is very critical to the future of internet as we know, right? It's going to be a very interesting video, and since IPv6 is a very big topic, we would be doing it in 2 videos. So we'll have day 24, that is today. This video will be on IP address, we'll look at basics, and then day 25 video, that video will have IP address, slightly advanced topics on IPv6, and of course we will also look at how to configure IPv6 in a Cisco device, right? So you know the drill. If you have not subscribed to our channel, please subscribe. If you have not liked us on Facebook, please like us and give us reviews there. And I'm also going to put in our social media links so you know where to find us on different platforms online, right? Without wasting much time, we'll get straight into today's class. The 3 things that we're going to look at today are the need of IP version 6. We'll look at IP version 6 address format, and we'll also look at IP version 6 address types, right? So if you remember in our IPv4 video a long time ago, when we started, some of y'all did not even know what an IP version 4 was, and then we went through that learning curve, and now most of us are very comfortable with IP version 6. So when we see an address like this, we are very comfortable, we know what we're talking about. Now today, IP version 6 is an address that is going to be like this, and all of us, if you're not very familiar with IP version 6, or if you have not worked with IP version 6, it is slightly daunting. For one, it's a very big address space, right? I mean, in IP version 4 dotted decimal, we had 4 decimal numbers to remember. Now if somebody told you, okay, XYZ, you know, Mr. so and so, this is your new IP address, and they say 2001 0 db8 8583 000 882e 03707 334, right? It's quite daunting. Well, don't worry, by the end of this video we will be in a much better position, right? So don't worry, take it as a challenge, and welcome to a lot of learning, right? This is going to be a very interesting video. The need. Why do we need IP version 6 in the first place, right? We learned IP version 4, we are happy with it. Today everybody is using IP version 4 and everybody is happy. Why do we need it? For one, IP version 4 is a 32-bit address, like we learned. So that gives us about 4 billion, was it? I don't know, whatever, the 2 to the power 32 number, right? So that's the address space. You only had so many IP addresses. But today, when they designed IP version 4, they thought that address space was more than enough. And if you remember the classes, we had class A, class B, class C, and class D and class E was reserved. So you had roughly about 75% of the IP addresses that was used or usable, and then they thought it was more than enough for the whole humanity, right? But today, in retrospect, we know that that was not so. IP version 4 would have, in fact, I think IP version 4 would have run out of IP addresses if a technology called NAT was not invented, right? NAT literally saved IP version 4. IP version 4 would have run out of address space at least 20, 25, 30 years ago. So IP version 6 had to be created, right? So they had another version. So you see why IP version 4 and then you run to IP version 6, because there's another IP like IPv1, v2, v3. They were all experimental versions. IP version 4 was the first production level IP protocol, right? Similarly, IPv5 was also experimental version, non-production version. IPv6 is what, again, it was an IP address that was released for production use, right? So IPv6 is a 128 address space. Now if you look at the numbers, 32-bit to 128-bit, 4 times, you would say. Well, if you know how 2 to the power numbers work, right? 2 to the power 32, let's say if it's 4 billion, 2 to the power 33 is double the number, right? So 2 to the power 34, if you add 2 extra bits, it's already 4 times the number. So IP version 6 address space is very large number. That is 2 to the power 128. Whatever that number is, that is the number of IP addresses that is available. That means to say that you can put IP addresses to everything, your cars, your phones, your watches. I mean, today's world, everybody, even a common man, they have a laptop with them. Most of us carry 2 phones. Then you have a smartwatch, then you have your smart home, you have refrigerator that connects to the internet, your TV that connects to the internet, you have your washing machine that connects to the internet. Almost the whole house connects to the internet. So with this new technology that Cisco is talking about, or of the new future that Cisco is proposing, is about Internet of Things. You must have heard Internet of Things, right? Internet of Things means everything in your life connects to the internet. Hence, they all would need an IP address. Now, with IPv6, that's possible because everybody can have millions of IP addresses, and still we would not run out of IPv6. Or at least I think today, we don't know what technology, how technology is going to evolve, right? I don't want to be the guy who told that the whole world would require only one computer, right? Right. So at the moment, if you look at IPv6, I think it's going to run for a very long time, right? Now, what is the IPv6 format? Like, it's a 128-bit IP address, and it is denoted by hexadecimal digits. So each of these letters or digits are 4 bits long, right? So this is 16 bits. Each of these 4-bit or 4 digits are 16-bit each. So totally you have the whole space is 128 bits, like we discussed, right? 128 bits. So every 4 bits, every 16 bit is separated using a semicolon, right? IPv4 was separated using a dot, and that was dotted decimal form, but here it's a hexadecimal. So hexadecimals, 4 hexadecimal colon 4 hexadecimal colon 4 hexadecimal colon. That's how it is. Now, it's not easy to remember an IP address this long, so there are some rules through which you can shorten the IP address. For one, rule number 1, it says groups of zeros can be abbreviated with a double colon, and this can be done only once per IP address. That means if you look at this, right, I'm going to take a different color, let's say yellow. If you look at this space, right, so you have 3 blocks of zeros. This block can be separated using 2 semicolons, right? So you have sorry, not semicolons, double colons. So you put 2 double colons. That means what is in between this space is blocks of zeros. Now, how many blocks of zeros? Now, if somebody gave you this IP address like this, FE80 double colon 5400, whatever that number is, how do you know how many blocks of zeros are there in between? Now, that is done by looking at the blocks. So if I give you this IP address, I know 1, 2, 3, 4 and 5. there's 5, but there's supposed to be 8, right? So 1, 2, 3, 4, 5, 6, 7, 8. So you need 8 blocks of 16 bit numbers. So you only have 5. That means this colon has 3 blocks, right? You with me? So this double colon has 3 blocks of zeros, right? So that's rule number 1. Now what's rule number 2? Rule number 2 says you can drop leading zeros, right? For instance, this number 04FF, right? That's the leading 0 can be dropped. So you can only write 4FF. So that's what is here. 4FF, nothing but 04FF, right? So if you use these two rules, you can shorten any IP addresses, right? So I know still this IP address, even after shortening, it is not really short, but we will look at some things as we go on this video. But for now, remember these two rules. These two rules are going to help you. All right, so let's take this opportunity to look at IPv4 header and IPv6 header. We did not have a chance to learn IPv4 header, but let's look at IP version 4 header first, and then we'll compare it with IP version 6 header. Now, if you see from this picture is something we got from the internet, and I think they have brilliantly summarized the difference between the two headers. Right, it's a very common image, but the color coding what they've done is brilliant. Right, so if you look at IP version 4, you see that IP version 4 is much more complicated and has much more information, whereas IPv6 is very straightforward, very little fields. And what you need to understand is if there are more data, router, now IP packet is layer 3 information, right? So a router, if it has a lot of information to look at, the router is going to take more time to process that data and do routing decisions. With less, obviously the router is going to be much more efficient. So that's why IPv6 is much more better, right? So what we need to understand is IPv6 header. First, this is 0, this is 31. That means the whole thing from here to here is 32-bit long, right? So IPv4 header by default, that is without this option, right? Without this option, it is a 20-byte address. It's a 20-byte header, right? So the header size is 20 byte. If it has options, the option could be more. So by default, the minimum length of a IPv4 header is 20 byte, whereas the minimum, IPv6 does not have a minimum. It has a fixed header size. It is 40 byte long. Right, 40 byte long is IPv6 header, and 20 byte long minimum is IPv4 header. So the first thing is 4, which denotes its version 4. The second one, IHL. IHL is the IP header length. IP header length, like we said, is 20 byte by default. If it doesn't have options, if it has options, it is going to be more. So if you look at, if you go to Wireshark, you will see number 4 version, and this will be number 5. Number 5 denotes that it has got 5 blocks of 4 byte each. So 0 to 31, 32-bit, that is 4 bytes, right? So 1, 2, 3, 4, and 5. 5 4-byte blocks, right? That is why you will have number 5 in IHL fields. Then types of service. Types of service is a field which tells if this packet is a special packet, if it's a voice traffic, for instance. Voice traffic obviously has more priority over data traffic, right? So if you have Cisco VoIP phones, then VoIP phone packets will have more. So this is a field which will tell if this is a priority traffic. Total length is the length of the header, that is 20 byte, plus you will have the payload. So payload could be all the data, right, that is being sent. So whatever that thing is, let's say this is, if this is 50 bytes, 50 plus 20 bytes, so this will be 70 bytes, right? So this is the length, right, length of the whole packet. Identification is a field that is used if to identify the IP packets, and more prominently it is used if the fragmentation happens. Let's say for instance fragmentation happens and one IP packet is being broken into 5, so the identification of all the 5 chunks of the data will have the same ID, and fragment offset, the first one will have 0, then 1, 2, 3 and 4, right? So that is what fragmentation offset does. So ID will be the same like I said, and fragment offsets would be the numbers that is used to refragment or reassemble those packets. Now flag is what will tell if it is fragment. So if let's say you don't want your data to be fragmented, there is a DF flag which is do not fragment. You can set that, and then that data will not be fragmented. And there is also another flag which says MF, that means more fragment. So if let's say for instance one IP packet is broken into 5, the first, second, third and fourth will have MF set to 1. The last packet will have MF set to 0, telling that there are no more fragments. That means this is the last fragment, and this fragment will say number 4, right? So the receiving device knows how to reassemble it. It knows the order. Fragment offset tells you the order of reassembling, and they can use it and to refragment. So one thing I want you to look at is the color. Whatever is in red is what has been removed from IPv6, right? Whatever is in blue has been what has been changed, right? Maybe some functions have been has been clubbed, whatever, but these are all been retained. Whatever is in yellow is exactly where it is. They've not changed at all, right? So this whole thing, identification flags and fragment offset, is like I said used for fragmentation. In today's world, fragmentation is something that does not happen, right? When IPv4 protocol was written many years ago, fragmentation was a very common thing because the medium was not very fast. It was not very reliable, so they had to break it down into smaller. So the maximum transmission units were much smaller compared to today. Ethernet standards, I think 1500 is the MTU value, the maximum transmission unit values are, right? So we don't need fragment or identification and flags in IPv6. TTL, we've discussed TTL many times. This is every time this packet goes through a router, they reduce the number of the number here, and when it becomes 0, they drop the packet because it is not going anywhere, so they're going to drop the packet. So that's maximum hops that it can actually live in the IP network. Protocol, like IP has UDP and TCP, so it tells which protocol is being used. And then you have header checksum. Header checksum, again we have discussed checksum earlier. If there are errors, this is the checksum that is going to identify the errors, right? So when you say errors, like I said, the data is being transferred as ones and zeros, 1 0 whatever, right? So any change, even this 1 bit changes to 0, that changes the whole meaning of this IP packet, right? So that's why checksum was required. But in today's world, it's very rare occurrence. Very rarely errors are induced on transmission, right? So that's why checksum is not there, part of IPv6. Source address, it's a 32-bit address, so you have 32 bits of source address, then 32 bits of destination address, right? And then of course you can add options and then and paddings. Let's say if like we know, everything has to be 4 byte long. So if at all your option is only 3 byte, right, you need to add zeros to pad it, and then you have 1 bytes of 0. That means it's going to be 4, and your IHL will change from 5, it will become 6, because now you have one more block of 32 bits, right? So that is how IHL is. Compare that to with IPv6 address or IPv6 header. Version is the same, it will be version 6. Traffic class, it's like your type of service. Flow label is similar to traffic class, but slightly more, where you give labels to the flow packets. Then you have payload length. Payload length is I mean, we had total length here. Total length is including a payload and your header, but in IPv6 we're not bothered about header length because we know it's always constantly 40 bytes, right? So only talking about the payload. Payload is what is the data that is coming below the header, right? So it is going to tell what is the length of payload. Then you have next header. Next header is a field that is going to tell what the next header is going to come. It could be anything, and it's more like protocol what we have in IPv4, IPv6. Even if if you have your own protocol, you can this is a field that will be able to identify and tell what is the next protocol that's going to come. So it is very, very usable in as the future technologies come in. Hop limit is comparable to TTLs, right? And it is a loop prevention mechanism, and 128 bits for source address and 128 bits for destination address, and that's how you get 40 byte of headers for IPv6. Now, like I said, IPv6 is much more simpler, so it's much more efficient for the router to make routing decisions using IPv6 headers. Address types and communications. Now, we know what unicast is. Unicast is when one computer or one device communicates with another device one-on-one. That is unicast. What is multicast then? Multicast is if many devices, right, at the same time communicates with one device. That is multicast. One device communicating with one device is unicast. One device communicating with multiple device is a multicast. Now, ideally, multicast is like a radio signal. Radio signal 92.1 radio FM station is there everywhere. If you want to listen to that station, you tune your radio or your car stereo or whatever to that frequency. Right. So similarly, if you remember from our routing video, rip routing version 1 used to send rip routing updates on a broadcast domain. That means it used to send it to 255.255.255.255. It was broadcast, or whatever that broadcast of that subnet was. It used to send it on that broadcast. But now version 2 would send it to a broadcast IP. Right, so only devices that was taking part in rip routing would listen to that broadcast IP and get updates, right? So that is multicast. And then there is another type of thing that you don't see in IP version 4 called as anycast. Now, what is anycast? Anycast is where you will have multiple devices with same IP address, and whenever you want to communicate with that IP address, the device that is closest to you would be sending you reply, right? So in internet, like we already have CDN network, content delivery network. So if you say you go to a website, right, youtube.com is not served, the whole world is not served from YouTube in California. YouTube will have multiple servers. You'll have Singapore servers. So if I'm in India and I'm going to YouTube, my YouTube request might be served from Singapore. You never know, right? So similarly, IPv6 actually has inbuilt mechanisms for having CDN, and that is using anycast, right? Right, there's one thing that's missing: broadcast, right? And broadcast is IP version 4 broadcast has been misused, right? So IPv6 said broadcast is not required, and they've taken broadcast away. It doesn't mean that broadcast has gone, so there's no broadcast. Multicast in IPv6, multicast would do almost everything that broadcast did, right? But in a much more efficient way. So broadcast as broadcast is not there, but multicast would do everything that broadcast did. Types of addresses, you have 3 types: link local, unique site local, and global scope. Now, what is link local? With IPv6, we need to understand that one thing that is primarily going to change is IPv4 we almost always used one IP address. One interface had one IP address. Let's say if this is a router and this is another router, you always had one IP address to these interfaces. Now with IPv6, the minute you enable IPv6 on an interface, that interface has automatically configures an IP address called the link local IP address. Link local IP addresses are IP addresses that start from FE80, right? And they're normally denoted by FE80 ::64. Similarly, you're going to have an FE80 ::64, right? This IP address is an IP address that is used only for local communication. Now, people who are from the Microsoft Windows world, we have very commonly seen this IP address 169.254.x, whatever that number is, right? We have seen this IP address many times. Now this is IP version 4's auto configuration IP address. That means if, let's say, this device is looking for a DHCP server. Let's say this is this has to get a DHCP IP address, and for some reason the DHCP server is not responding back, right? DHCP request is not coming back. This computer has a mechanism inbuilt by Microsoft that it can give an IP address to itself. So it chooses an IP address 192.169.254. Let's say 1.1, right? It gives itself an IP address. Similarly, on the switch, let's say this is a switch, right, whatever, that's a switch, and this is also another device that also is looking for an IP address on a DHCP, and it also is not getting an IP address. It gives itself a random IP address. Let's assume it gives the same IP address 1.1, and it sends an ARP request on the network asking a broadcast asking, is there somebody with this IP address 169.254.1.1? and this device will say, yes, I am 254.1.1. so this device will again do another random number 10.10, whatever, and then again it sends an ARP, and if nobody responds, it says, okay, I'm going to take this IP address of 169.254.10.10. Right now, if you look at it, it doesn't have DHCP. It's configured for DHCP. Because DHCP is not giving it an IP address, they have auto-configured an IP address to themselves. Now, technically, these both devices can communicate with each other because they are part of the same network. Right? This is auto-configuration. We have seen this many times, but we never ever used it. Right? Similarly, in IPv6, there is a link local IP address auto-configured with starting from FE80 and ::64. Now, what is FE80 ::64 and how both of them can have the same IP address? Now, if you remember slash notation, right? IP version 4 slash notation, whenever you see /64, that is where the division between network and host happens. So that means if /64, the first 64 is network and the next 64 is host, right? FE80 : that means it is FE80 and 000, and then there is a host part, right? So this host part is different for this device and it is different for this interface, right? Now this is automatically configured. Now how do they configure this part? That is using the MAC address, right? So MAC address, as we know, is a 48-bit IP address or a 48-bit number, right? That is 1 2 3 4 5 6, right? So this is 6 blocks of you have 6 blocks of hexadecimal numbers, like you have 2 hexadecimal : 2 hexadecimal : 2 hexadecimal. This is the Microsoft way of denoting it. I think Cisco denotes by 4. You have 4, 4 and 4. You have 3 blocks of 4 hexadecimal numbers, right? So let's do the Microsoft way. So it is 1 1 2 2 3 3 4 4 5 5 6 6. This is the MAC address of, let's assume, this interface. How it generates is, it takes the MAC address, it breaks it into 2. So you have 6 hexadecimals on the left and 6 on the right, and in between it adds FF and FE. So it adds this FF and FE and it creates a 64-bit block for the host IP address. Now you know this part 1 1 2 2 3 3 4 4 5 5 6 6 is a MAC address, and MAC address is unique for every device. So every device has its own MAC address which is unique by itself. In between it just puts FF FE, and you have a unique number now which is unique to this device, right? Very cool, isn't it? Right? So this is how it creates its own link local IP address, and link local IP address is used only for communication in between this segment, right? It can't use that IP address or that link local IP address. It cannot use it for communicating outside that segment. This is used only for that segment, right? Next we have is the unique site local scope. Now unique site local scope can be compared to our private IP address. We had a private IP address 192.168.1.1, right? Private IP address and public IP address. The reason we needed private IP and public IP was because of the invention of a technology called NAT, like we discussed. Unique site local scope is a technology, or is a scope that gives a private IP address. Now you'll ask me, Imran, you said every device can have an IP address. That's why we're moving to IPv6. Absolutely right. Every device can have that. But some people are so used to this private IP concept because of security. They say because NAT acts like a natural firewall, outside devices does not have direct access to any of the device inside the NAT. Which is fair to say, but NAT creates a lot of trouble. NAT creates a lot of trouble, for instance, with VPN. ESP protocol, for instance, right? Cannot, I mean, it has a lot of trouble with NAT. Like if I mean, it's not part of our syllabus, so I'm not going to discuss much about ESP and ISAC-MP. I mean, IPsec protocol suite would love if NAT was not there, because it becomes much more easy. So IPv6 has IPsec part of its IP suite, right? Where IPv4 had to have an IPsec security protocol suite to create VPN traffics, right? Now with IPv4, that V6 security comes inbuilt, right? And global IP addresses becomes very easy. But because some people still want that, there is a type of IP address called as a unique site local scope, which is an IP address that is relevant to an organization. Then you have an IP address, the global scope, that is comparable to our public IP address, right? Unique local scope, some people are arguing we don't need it. Everybody's going to go with global scope and linked local scope. Some people are saying we need it. So we're just discussing that. Finally, I think we will most probably, I have a feeling that we will go without this, because I mean, you have much more benefits by having global scope and every device. For instance, mobility, right? I can have the same IP address whether I'm sitting in Bangalore or I'm sitting in New York, right? The IP address will not change to my device, and I can have mobility becomes standard. I mean, I can go sit anywhere in the world and start using all my network devices, network access, network drives. Security is definitely one aspect, but IPsec is going to be part of it. So you can literally have security VPN tunnels, that is from wherever you're sitting to your office, and have access to all your devices. Naturally, now we need to have external mechanisms to create that VPN tunnel for you, but maybe with IPv6 that tunnel is going to be standard, right? So there are a lot of things that can happen, that will happen. It's something that we will wait and see, but this is what it is. I think there's too much information that we shared in today's video, so I'm going to cut it here. Remaining we will do in the next video. So what I would ask you is, if like for a homework for you, is go learn hexadecimal. I think if you want to master IPv6, your hexa to binary conversion must be top notch, right? So like F111, you need to know it's F. I mean, go search, you do a Google search on hexa to binary conversion, and there are multiple resources that you can get. But by the time you watch the next video, I would say get your hexa to binary practiced. If you don't know, learn it. If you know, just practice it, right? That will be a homework for today. And since we covered a lot of topic in today's video, I would ask you to go watch this video a couple of times, because you need to understand. There's some topics that you need to understand before we go ahead, and IPv6 is going to be very relevant in your networking career as you go from here. So start becoming an expert in IP version 6, right? So thank you so much for watching. If you have not liked our video, please dislike. You have the thumbs down, click on thumbs down. If you loved our video, of course, like it. Feel free, like it if you like it. Don't like it, don't like it, dislike it. But whatever it is, press that button and give us that subscription, right? If you want more videos, this is the place you need to come. So subscribe to our channel, and thank you so much once again, and I'm going to see you very shortly.